Well, it's a pleasure to be here. At my age, it's a pleasure to be anywhere. In fact, I like to teach using the blackboard, but I realized this morning that teaching using the blackboard here is a daunting physical task, which I may or may not be up to. I hope I'm up to it. I'll probably need an eraser. No. You're not understanding me.
A person to erase.
Yes. So, Ahmed, will you be my eraser?
Sure.
Good, okay. All right. I just realized I'll probably also need a hooker. Cancel that? Cancel it. Ying's wondering what I said. Okay. You'll also be my hooker if necessary. Okay. Okay, complexity is a hard mathematical subject, and as most of you know, I'm not a real mathematician by any means. As I think it was Scott who said, I overheard his lecture at home, I listened to it, and he said that I said, which I did say, I don't do proof, Scott. And it's, it's largely true. I don't try to prove things. But in this particular case, I think it's sort of doubly true that it would be a mistake for me to try to prove anything I say, for the simple reason is that nobody can prove anything about complexity practically. What you can do is you can say, I conjecture this, and I can prove that that's the same as a conjecture that, but neither conjecture can you prove. And so complexity is a subject which is very, especially difficult to prove anything in. And I think to say at this point that I wouldn't move forward if I can't prove what I said would be very counterproductive. It would be like saying I won't use QCD until I can prove it confines. To this day, nobody can prove that it confines. And so if we want to move forward, we have to use other techniques. My own technique for doing physics has always been close your eyes, try to visualize the answer, and then say that's what it is. No, that's not really true. What I try to do mostly is to find collections of, visualize the phenomena, yes, you don't have to close your eyes, visualize, get into the bathtub, visualize the phenomena, and not just the phenomena that you're trying to understand, whether it be mathematical or physical, but to try to visualize a collection of different phenomena which are related in some way and which tend to reinforce the same view until you come to the conclusion, look, if this were wrong, so many things would be wrong that I would have big problems. And I'm quite serious about that. And the other technique is the one that Sherlock Holmes always used, which, how did it go? When you have eliminated everything that's impossible, what remains must be the truth, no matter how improbable. For me, the connection between black holes and complexity was a highly improbable idea at first, one which, after thinking about it for years now, I just feel like there is no other alternative. It has to be right. Although I would have to admit the precise form in which it's right still remains to be given. Exactly what we mean by complexity and its connection with black holes is still a work in progress. I think it's an extraordinarily interesting work in progress because I think it has more to do with the interior of black holes than anything else I can think of. Well, why should we be interested in the interior of black holes? I think everybody here would say you don't really understand the black hole until you understand what its interior is. And you really don't understand quantum gravity until you understand horizons. Okay, so I'm going to start with, today, for the most part, just discussing complexity. I'm not going to discuss black holes at all. And I want to begin with why is complexity so important a subject in quantum mechanics? And I would say the reason is one that was pointed out by Feynman many years ago, that Hilbert space is enormous. Hilbert space is much, much bigger than spaces of classical problems and so forth. And I want to begin by quantifying that. Now, I hope I can figure out how to use the blackboards. Let's start with k qubits, a space of states which is 2 to the k dimensional, and let's write down a general state. Psi equals sum from 1 to 2 to the k of a collection of parameters, a collection of complex numbers, alpha I. How many complex numbers? 2 to the k of them. Now, what I want to ask is how big is the space? By that, I don't mean how many orthonormal vectors are in it. I mean how many states are there altogether? Well, that's a stupid question, you say. There's a continuous infinity of them. You have a continuous infinity of the alphas. Okay, let me try to regularize it by saying let's pick the alphas from some discrete finite subset of possible alphas that I could put in there. Not that I think that that has anything to do with quantum mechanics, but just to try to make a counting if I were to regularize alphas and say that alpha, any one of the alphas, can be anything of the form alpha 1, alpha 2, let's say up to alpha m. M complex numbers, and ask how many states there would be then. And the answer is pretty clear. It would be m to the 2 to the k. 1 m for each parameter, 2 to the k parameters. This would be the number of states. Let me call it number S. Number of states is m to the 2 to the k, which is also equal to 2, wow. First of all, it's interesting just to put in some numbers. Supposing m is 4, a very, very modest number. And let's suppose k is 4. K qubits, 4 possible. You know how big that number is? It's about 4 billion. Okay? It grows fast. 4 billion possible states. So let's take the logarithm of it, which may be a little more manageable. It is. The log of the number of states, which would be about 22 for the same numbers there, that's equal to 2 to the k log m. Now, there's a pattern here that I want you to remember. The pattern is, first of all, this is only the logarithm. But, all right, log of the number of states, 2 to the k log m. It's still very, very rapidly growing with k. In other words, very, very sensitive to k, but very weakly sensitive to m. Very weakly sensitive to the cutoff parameter or the way of regularizing, but still very, very rapidly growing with k. That's a pattern I want you to remember. Let's try to do a more precise counting. Here's the way we'll do more precise counting. What is the space of states of a k-qubit system? By now, I don't mean the linear Hilbert space. I mean the manifold of normalizable states modding out the U1 phase. It's some CPN. Where n would be 2 to the k. I'll put that in later. CPN. Let's try to count how many points there are in CPN. Well, there's again a continuous infinity, so I've got to regularize it. Here's CPN. Let me put CPN over here. You people will have to. Can you see this? Doesn't matter because I'll say it. Here's CPN. That's it. Looks sort of like a sphere. I'm going to introduce a regularization by filling it with little epsilon balls. An epsilon ball is a ball of radius epsilon. How many, and I'm going to identify states with epsilon balls. In other words, we're sort of coarse graining, not distinguishing this state from this state from this state from that state and so forth. Ask how many epsilon balls are there in CPN. as a function of epsilon. We can do that calculation. You can calculate the volume of CPN. Here's the volume of CPN. I'll just write it down. Volume of CP. It's basically the volume of a sphere with the same number of dimensions. The number of dimensions is twice n, because n is a complex projective space. CPN, it is pi to the n divided by n factorial. Keep in mind, n is not the number of qubits, it's just the dimensionality of the space, the dimensionality of the CP, and n is 2 to the k. N will be 2 to the k minus 1 for k qubits. Okay, let's compare that now with the volume of a epsilon ball. Let's call it just VB for ball. It happens, it's a volume of a ball of the same dimensionality of CPN, in other words, 2n, 2n real dimensions. That just turns out to be pi to the n over the same n factorial times epsilon to the 2n. Again, 2n because the real dimensionality of the space is 2n. Okay, so the number of epsilon balls in CP then is just 1 over epsilon, I'll call it the number of states. Same as I called it up here, so number of states. I really mean the number of epsilon balls. That is 1 over epsilon, I think it's to the twice 2 to the k minus 1. I've used that n is 2 to the k minus 1. Everybody know where that comes from? The dimensionality of the Hilbert space is 2 to the k. You subtract 1 for a reason I can't remember, and that's it. Okay, again, the logarithm of the number of states, log number of states, is equal to, approximately equal to, or of order. I'm going to drop this 2 here because it's not important to me. 2 to the k log 1 over epsilon. Same pattern, very rapidly growing with k, very weakly dependent on the regulator. Okay, so that's the pattern that I want to call attention to. Now, all of this, the spaces are huge. All of this sort of begs the question, how, in some sense, big is the Hilbert space in a different sense? How far apart can states be in this space? Okay. What's the maximum distance? What's the diameter of the space in the sense of how far apart can states be? And to answer that, we have to have a clear idea of what we mean by the distance between states. One notion of distance is, where's my hooker? Am I doing this right, Douglas?
Looks good.
Good. All right, one notion of states is just the inner product distance. Distance between A and B is just equal to the arc cosine, ARC cos, arc cosine of the absolute value of the inner product. That's the standard inner product metric, okay? With this metric, the space is small. It's small in the sense that the maximum distance between any 2 points in it is pi over 2. They cannot be further than pi over 2. D max, I'm not going to write it down. D max is pi over 2. On the other hand, that seems a little bit ridiculous. Let me compare 2 kinds of different states. So I'll make up a story. I have a car, it's an old beat up Ford. In fact, it's pretty much just a rust pile now. My wife has a car that's a brand new Mercedes-Benz. This is not true, incidentally. All right? She has a car which is a brand new Mercedes-Benz. Now, her Mercedes-Benz is very up-to-date. It has an ignition switch that consists of one qubit. One qubit. It's either on or it's off. Now, don't ask me what happens to the car when it's in intermediate superposition. Okay, my car is just a pile of dust. Let me ask for two different senses of definitions of the distance between states. First is the distance between her car when it's on and off. Well, it's very easy to make a transition from the car on to car off. You just flip one qubit. That's easy. So in that sense, the states are close. It's also easy to make a superposition of such states, transitions, superpositions, and also, if you wanted to make a superposition of states and then measure the phase. It's easier, just a single qubit. I think Scott talked about this a little, the idea of relative complexity. I don't know, maybe he didn't. Maybe you didn't listen to him well enough. I know I have a hard time listening to him. No. What?
That'll be on the video for Scott.
I know, I watched it. Okay, so where was I? Yes, the pile of, all right, now compare that with the distance between her Mercedes, brand new, and my Ford, which is a pile of rust. 1929, I think. Okay. In some sense, the pile of rust is much further from the new Mercedes than the Mercedes on or off are distant from each other. But the distance in the inner product metric is the same, pi over 2. So that metric does not show, in some sense, the qualitative distance between states. The other notion of metrical distance between states, it's called relative complexity. It's a new subject. It hasn't existed up till now. People have not pointed it out very much. How do we quantify the difference between the Mercedes and the old Ford? Okay? You quantify it by the number of small steps. We assume that in quantum mechanics, or physics in general, in quantum mechanics, that if you want to change something from one thing to another, you do it in small steps. The idea of applying a single unitary operator to a Ford and making a Mercedes out of it, that's too hard. So you first change this little piece, and then you change that, and you change that. That brings us to the idea of quantum circuit. Okay, so quantum circuit, let's put a circuit here. We'll assume all of the cars can be represented as collections of qubits. Time flows horizontally here. This is a collection of qubits. And how do you change a state A to a state B? You do it in steps. And, for example, the steps could be gates. Gates just mean little unitary operators which involve small numbers of qubits at a time. And you simply apply them until you get to B. I can write an equation for that. Let's write an equation for it. The equation is that A is equal to Gn, Gn minus 1, down to G1 on B. Okay. Where G's are simple gates. Now, in doing this, you have to choose a collection of gates that are allowable. You choose your collection of gates. If you've chosen it well, then that, in fact, if you just chose it more or less at random, the gates will be universal in the sense that you can get from any B to any A by multiplying enough of these. Not quite. You can get from any epsilon ball to any other epsilon ball, no matter how small epsilon is. Okay? That's called a universal collection of gates. And now we can ask, what is the minimum number of gates? Not the way you might actually do it, but what is the absolute minimum? Yeah. Oh, I probably did, but that's okay. You can go from one to the other just by inverting the G's. So let's assume that when you make a universal choice of gates, your gate set contains not only G, but G inverse, or G dagger. Then it doesn't matter. Okay. All right, so that minimum of n is called the relative complexity of A and B. And again, up to tolerance epsilon. Okay. Now, I want you to think of that this following way. Let's again draw our CPN. I don't see CPN anymore. Oh, yeah, here's CPN. And let's suppose that this is A, and this is B. Then the sequence of gates is a path from B to A. It's a kind of discrete path. It's a discrete path from B to A, but it's also the minimum, also the complexity, the relative complexity is by definition the minimum of such gates. So you can kind of think of it as a geodesic on this space, but a geodesic with the right definition of measure, with the right definition of distance. It's whatever this relative complexity is, it's some kind of metrical notion. I won't yet call it a metric, but it's some kind of metrical notion of distance between states, and relative complexity is kind of the geodesic distance of the shortest geodesic between them. That's a theme that we'll come back to over and over, and I do believe it's the right way to think about complexity. Okay, I think one of the reasons that people have not had powerful ways to think about complexity, and in particular for connecting it with physics, has been an insufficient appreciation of its geometric character. And that's what we'll talk about today. Okay. Now let's talk about not states, but let's talk about unitary operators, unitary matrices on the space of states. I'm going to erase this. I don't think we need it. Unitary matrices have two different incarnations, if you like, in what we'll talk about. One of them is as operators. So let's just write a unitary operator is equal to uij, that's the matrix representing u, times I times j. That's u as an operator. U also can represent a maximally entangled state of two systems. All you have to do is write that the state is equal to uij, I for one system, and then j, and it's normal to conjugate it. Conjugate it means to basically to time reverse it. Okay, so the same operator here represents both operators, and so whenever we're talking about distance between operators, we're also talking about distance between maximally entangled states. If this were delta ij, then this would just represent a product of Bell pairs. Product of Bell pairs, 1, 1 plus 2, 2, just a product of Bell pairs. Okay. All right, so there we are. That's what a unitary is. And now let's talk about the distance between two unitaries, u and v. Same idea. There's the inner product distance. First of all, the inner product distance is before we do that, let's count. Let's see how big the space is, the space of unitaries. Supposing each matrix element, now how many matrix elements are there? There are 2 to the k, 2 to the 2k matrix elements. The space is dimension 2 to the k. The number of matrices is 2 to the 2k. To make them unitary, you have to put some constraints on it, but the number of constraints is much smaller than the number of matrix elements. And now let's suppose each u can take on one of a set of complex numbers, the same m, then this is how big the space of unitaries is. M to the 2 to the 2 to the k. It's even bigger than the space of states. We can do better. We can do an epsilon ball job on it, the same kind of epsilon ball counting. I'll tell you what the answer is. You first calculate the volume of the unitary group of dimension 2 to the k. And then you calculate the radius, the volume of an epsilon ball of the same dimensionality. You divide them, and I'm going to give you the answer. Let's call it the number of unitaries. Number of units of number of unitaries turns out to be 2 to the k over epsilon squared, all to the 4 to the k over 2. Huge, tremendously large when k gets to be bigger than a few. Okay? The logarithm of the number of unitaries, log number of unitaries, is equal to 4 to the k, same 4 to the k. Oh, this is, of course, m to the 4 to the k. 4 to the k, where's my answer? Times k log 2 over 2 plus log 1 over epsilon. Same pattern. It depends ferociously on k and very weakly on the regulator. Okay, good. So roughly speaking, let's just call this 4 to the k unless we're especially interested in the epsilon dependence. And we'll call the number of states 2 to the k. Okay, what about the distance between unitaries? Let's call it duv. Again, there's an inner product distance. It would just be the inner product of the states, the maximally entangled states. That's just arc cosine of trace of u dagger v. Whenever I use the symbol trace, I will always mean the normalized trace. Normalized trace means that the trace of the unit matrix is 1. I don't have to write a denominator there then. So my definition of trace, some people put a symbol over it, but I'll just use trace. Trace means normalized trace. This is the usual definition of the inner product, or inner product distance, and then there's the relative complexity of u and v. And what is that? That's just starting with u or starting with v. Let's start with v. Multiplied by a product of gates, simple gates from within n minus 1, to 1. And sorry. C of uv means the minimum n that can satisfy this equation here. Minimum number of gates, minimum number of steps, very similar idea. Instead of a and b here, just put u and v. And again, we can think of geodesics, but not in the space now of states, but in the space of unitaries. Okay. Any questions? It doesn't matter because I can't hear you anyway. I'll try though. No questions? Okay, good. Yeah.
So are there any assumptions on what kind of G's we want, like, or this is to call any G?
First of all, the unitary. Good question. Okay. I've drawn circuits as if they were composed out of gates only involving 2 qubits. Okay. That would be called 2 local. 2, not TOO local, but TWO local, 2 local. I will always assume that a gate is a k local thing. In other words, it involves at most k qubits where little k is much bigger than big K. Having said that, I will probably wind up using little k equals 2 for almost everything I do. If I were doing SYK, I might do little k equals 4, or I might even let little k equal little q. If you don't know SYK, don't worry about it. But gates are things which are made out of small number of qubits, much smaller than the total number of qubits. Okay, so that's the idea of relative complexity, and it plays the same role as relative complexity of states. Very, very different maximally entangled states will still only have an inner product, which is at most pi over 2. So and with the inner product metric, even this unitary space is in some sense small, high dimensional, but it has a small diameter, whereas the relative complexity can be very large. How large can the relative complexity be? Well, we'll do a calculation at some point, but I will tell you the relative complexity can be as big as 4 to the k for unitaries and 2 to the k for states. So huge. These geometries defined by these two metrics are extremely different, and we'll discuss how different they are. But next, relative complexity, I'll take the case of unitaries, is a metric. Let's see what it means to be a metric. It first of all means that C is greater than or equal to 0. That's true. There's no way you can have a negative number of gates. So C is greater than or equal to 0. C of UV is equal to 0 if and only if U equals V. This is true. The only way you can have no gates connecting U and V is if U is equal to V. It's symmetric. Now here I have assumed that if you have an allowable gate, its inverse is also an allowable gate. So that allows you to solve for V. And finally, the triangle inequality. C of U and V is less than or equal to C of UW plus C of WV. Why is that true? Well, one way of getting from U to V is to pass through the intermediate W. If it takes a certain number of gates to get from U to W, and a number of gates from W to V, then you can surely get from U to V by the sum of the number of gates, and possibly a smaller number, okay? So, triangle inequality, these are the conditions that a measure of distance is a true metric, and so relative complexity is a metric. What else can we say about it? It has a special feature of being what's called a right invariant metric. Anybody know about right invariant metrics? Okay, anybody know about left invariant metrics? We don't have a mathematician who studies left invariant metrics here? Well, just in case there is. Right invariant metrics are the same as left invariant metrics, except they're right instead of left. Okay. What is a right invariant metric? Okay. So let's take this equation here. Where is it? That, how did I write it? W is equal to Gn dot dot dot. Let's just call it capital Gn. Capital Gn stands for this string of gates here. Capital Gn on V. No, U. My bad, U. Okay, that's that equation written down here. Okay, now let's multiply it on the right by W. W is another unitary operator, any unitary operator. This says that if U can be connected to V by n gates, then UW can be connected to VW by the same number of gates. That says that the relative complexity of UW and VW is the same as the relative complexity of U and V. That's called right invariant on the multiplication from the right. Let's see what happens if we multiply from the left. All right, this says right invariant. Yes, right invariant. Check. What about left invariant? Left invariant, we multiply on the left, equals W. Well, I don't want this W here now. Let me insert in here W inverse or W dagger, W times V. Well, WU is equal to something on WV, but in general, conjugating a product of gates by an arbitrary unitary matrix does not give a product of gates. This object will in general not be a product of n gates, and so it follows that the relative complexity of multiplication from the left multiplication from the left is not an invariance of the relative complexity metric. Not. Okay, any questions up till now? Yes?
What was the unit ball in the...
Say it again?
The unit ball in this relative entropy metric look like compared to our epsilon balls that we're used to?
Are you asking me how do epsilon balls affect this?
Oh no, it didn't affect it. It's just two different metrics in the space, right? So like...
Two different metrics.
How spread out are these?
The epsilon balls I will always take to be epsilon balls in the inner product metric. That's a convention, but we'll always do it that way.
Like in terms of something that's like a single gate away is like somehow, like what is the geometric picture of like something one k-local step away?
I'll come to it. I'll come to it. It does not mean close in the inner product. And close in the inner product does not mean close in the complexity metric. So they're very incommensurate kind of things. But we'll come to that. Okay. My conclusion out of all of this is that complexity has a geometry to it, and that the study of complexity is a branch of geometry. It's the branch of right invariant geometries on the space SU2 to the K. Right. Not widely studied, except by Michael Nielsen a little bit, and by me and Adam Brown a little bit. Okay, now I want to come to graph theory. Graph theory is a mathematical theory. Again, it took me a long time to penetrate the lingo of it, but I understand it now. And I'll tell you how this is connected to graph theory. Let's see. I'm afraid I'm going to screw up the blackboard technique. Let's see, I guess I can go over to the last blackboard. Ah, my eraser. Thank you, eraser. Ah, and also my hook. All right. What I'm going to draw now is it looks like a graph, but it's not the graph in the sense that I mean, you're watching him, you're not watching me. Okay. He's more beautiful than I am for sure, but yeah, we can get rid of that. Okay. Now I'm going to draw something that looks like a graph, but it's not a graph, it's a circuit. All right, so I'm going to define the standard architecture for circuits. This is a definition. Standard architecture for circuits. 1, 2, 3, 4, 5. I always want an even number of qubits. What we do, time goes to the right. We divide things up into time intervals. I'm going to call each time interval delta tau equals 1. Now I'm going to give you a little secret right now when it comes to black holes. This time, which is the time of the computer, the clock that separates intervals, is a particular kind of time in black holes. Anybody know what it is? Is it Schwarzschild time? It's Rindler time. And I'll show you why as we go along. Okay. You know what Rindler time is? If not, I'll try to tell you. All right, we divide up the circuit in that way. And the rule is, in each time segment, every qubit gets to interact once. That means there's going to be k over 2 gates. 1 gate, 2 gates, 3 gates for 6 qubits. 1 gate, 2 gates, 3 gates, and so forth. That's the rule, but on the other hand, any pair of gates, any pair of qubits can interact. This is called k-local, but all-to-all. Everybody can interact with everybody else, but in small groups. Right? This is the standard, I'll call this the standard architecture for quantum circuits. And notice we can count the number of gates that acts. It's equal to the total time that elapses times k over 2. K over 2 times the elapsed time is the number of gates that's happened. This would be called a depth 3 circuit. Depth means how many layers you have. Width 6, and k equals 2. That would be this. That would specify this kind of circuit. Now, this is not the graphs that I'm thinking about. Now we come to graphs. First of all, how many distinct kinds of depth 1 circuits are there? How many distinct kinds of depth 1 circuits? The first thing I have to pick is which qubits to pair. So the first question is how many pairings are there? Then you multiply that by the number of allowed gate types. The number of allowed gate types, that's small. That's not going to make a big difference here. The main thing in counting how many different kinds of depth 1 circuits are there is the number of ways of pairing. You can fill in the details if you have a number of different gate types. Okay, how many ways are there of pairing k things? Let's say ordered pairs. Anybody know the answer? It's k factorial divided by k over 2 factorial. Took me half an hour to figure that out. Adam figured it out in 10 seconds. This is the number of single-step circuits, and I'm going to call that, incidentally, this is approximately equal by Stirling to the k over 2. There's some e's and pi's, but they're not important. They're very subleading and not important. It's essentially k to the k over 2. That's the number of types, and I'm going to call that d, little d. Little d is an odd notation, but it's used by graph theorists to define the degree of the graph. The degree of a graph is a number of edges that comes out of each vertex. All right, so now here's the idea. Here's SU2 to the k, just abstractly. Don't pay any attention to its geometry. Geometry is not important. But we start at the center. What is the center? The origin, the unit operator. We start at I, and now we start applying gates. I'll say this, the complexity, not the relative complexity, the complexity of a unitary operator is the relative complexity relative to I, which just means its distance in some sense from the origin, with the origin being I. Okay, how many choices for the first layer do we have? Well, we have D of them. Let's lay them out here. Here they are. Don't pay any attention to where this actually falls into SU2 to the k. It's just a decision tree. Which of the possibilities will you choose for your first layer? What I'm doing is I'm drawing a graph that represents all possible circuits. Okay, how many of them are there? There are D edge ends, and that means D unitaries have been gotten to. Now, could some of these be the same? Could you have gotten to the same unitary by different short circuits? I'm going to say no. This is the principle of no collisions, that you don't wind up in the same place. And why should that be true? The reason is because of the very high dimensional nature of the space. The likelihood that two different circuits, two different single layer circuits will get you to the same point is very low. You can compute it. I don't remember what it is. It's exponentially small. Maybe it's doubly. I don't remember for sure. But it's very, very small that 2 points will hit the same spot on SU2 to the k. Okay, so that's first, no collisions. We'll adopt that as a provisional principle, but not a permanent principle. Now, let's go to the next layer. We're growing the circuit a little bit. Each one of these points can now go to d minus 1, 5 in this case. And so it goes, on and on and on. Circuit, as the circuit grows, as the circuit is allowed to evolve, the tree gets bigger and bigger. Okay? This tree is a graph. That's what I mean by a graph. Okay. How many, assuming no collisions, how many states do I get to after depth 2 circuits? Well, the answer will be d squared, and that will be k to the twice k over 2. How about depth d? Let's imagine we go a depth d. That will just replace this by d. K to the dk over 2. Now, dk over 2 is nothing but the number of gates up to that depth. K over 2 times depth d. And what I'm going to say now is if there truly are no collisions, then when you get to this point over here, you have gotten to that point in the shortest possible way. Suppose there was a shorter way, which meant, for example, maybe you got to it over here, then you would have a collision between this point and this point. So if there are truly no collisions, we can, up until the point where there are collisions, we can just count the number of gates and call that the complexity, because it will be the minimal number of gates that get you there. How do I know that? That is the assumption of no collisions. dk over 2 then is the complexity of this circuit. Let's call it C, which I will also write as e to the complexity log k. Apart from this log k, what this is telling me is that the number of states or the number of operators with complexity c grows exponentially with c in this manner. If I just ask what is the number of unitaries with a given complexity, the answer is it grows exponentially with the complexity. Okay? Keep that in mind. It's a fast growth. Okay? So most unitary operators have very high complexity because it's growing so fast. This is a clue about the nature of the geometry. I want to compare this with something. When you have a tree like this, you can just forget where it came from and just think about the abstract tree, and you can think about particles hopping around on the tree. An actual quantum circuit evolving would correspond to starting someplace, hopping to someplace else, hopping to someplace else, hopping to someplace else. Let's take an ensemble of these. We take an ensemble of starting points. So we have an ensemble of circuits. Each one of them may evolve differently than the others. They all start here, and they grow and they fill up this tree. Incidentally, the subject of random walking on a tree is a very well-developed subject. Here there are lots of theorems. Okay, so we have this ensemble of things. We have that the number of configurations of one of these particles on this tree grows like e to the c, which means like e to the distance. I maintain that this same formula represents, you can think of a gas growing, that C log K is nothing but the entropy of this gas in the following way. Let's just write this differently. Let's write the volume, I'll call it the volume, which means the number of states. The number of states, or the number of unitaries, with complexity C grows like this. If I solve this, I find that the complexity is the complexity times log k is the volume of the configurations, is log of the volume. Now, sorry. Yeah, log k times c is log volume. This is very similar to saying that entropy is like the logarithm of volume in phase space. Okay. So if I had such a gas on this space here, I would identify the complexity or the distance from the origin as a measure of the entropy of those configurations at a certain distance. This, I think, is an important thing that, as far as I can tell, has been completely missed by complexity theorists, that complexity is a kind, or this quantum complexity is a kind of entropy. It's not normal entropy. These are not orthonormal states here. We're not doing we're talking about something different, and I'll come to what it's different, but it is a kind of entropy. It's a measure of the number of states with a given complexity. Okay. That is why there is a second law of complexity. In fact, just looking at this graph, just look at this graph. Supposing you found yourself over here after two layers. What's the most likely thing to happen next? To move out or to move in? By how big a factor? Large. Whatever d is, or d minus 1. So there's a very strong tendency to move out. Why? Because just the number of states grows so rapidly with complexity. So the tendency for complexity to grow is just this fact that the number of states with a given complexity grows fast, and that's very, very similar to the second law of thermodynamics, where normally entropy is the logarithm of a volume in phase space. The bigger the entropy, the volume in phase space grows exponentially with entropy. So I've harped on that because I think it's a very important point. Good. Okay. Any questions about anything up till now? Yes.
Is there any independent literature on I guess dense discrete subgroups of SU?
What's that?
Like some sort of discrete subgroups of SU to the K, like some sort of dense discrete subgroup. That's essentially what you're having, but the distance is how many times you iterate and you never go back to the same point because the basic gates are just letters.
I think there's very little literature about this, but of course there is a lot of literature about the relation between groups and graphs like this. These are Cayley groups of...
Yeah, but this should be some subgroup that has just an infinite number of elements.
We'll say it again?
Like by acting with some basic sets of unitaries, you're just going along the group manifold and filling out some subgroup that is somehow dense because you want.
We're going to talk about that. We're going to talk about that. We're going to talk about that. Is there literature about it? I suspect there is. I can tell you, for me, it's been a nightmare to penetrate what literature there is on this. It's all in this math speak lingo that I don't speak. And so I've had to mostly sort of seat of the pants, guess my way through it. And that's what you're getting. Yeah.
So does the notion of relative complexity somehow capture?
Does the notion of?
Relative complexity somehow captures trace distance or fidelity?
Does the notion of complexity capture?
Does it capture?
No, the complexity of an operator is the minimum number of steps. Well, it's k over 2 times the minimum depth of a circuit that will get you to that unitary, minimum. Okay? With the assumption of no collisions, then the unitary that you get to over here, you've got to in the fastest possible way. So the complexity at the, let's call these the leaves of the trees are the endpoints of the trees. At the leaf of each tree, there is a unitary, right? That unitary has a complexity, and that complexity is just the distance along the tree to the point, the graph distance, times k over 2.
So we have this concept of fidelity or trace distance in quantum.
I'm having trouble hearing.
We have this concept of fidelity in quantum complexity, like trace
Yeah.
distance or fidelity.
Yeah.
Is this somehow?
So that's this DUV, basically.
That's
Yeah.
Yeah. So he's asking about the difference between DUV and relative.
All right, I'm about to tell you that the difference is huge. And let me tell you in what way. There are two extremely different geometries on the same space. Okay, let me draw, I'm going to describe this by drawing a picture. No equations, just pictures. First of all, we have one geometry, which is just it's an abstract decision tree. And it's just, it's just a tree. You know what I mean. Good. It's just a tree, and it's an abstract space. And this space has the quality of growing exponentially as you move away, and it has the character that the complexity relative to the origin here is just the distance multiplied by k over 2. Now, here is SU2 to the k. It doesn't really look like a sphere, but I have no other way to draw it. And let's map it. We start here at the origin. Let's put the origin over here. And now we go one step. We're fairly likely to get to something which is almost orthogonal to the original u. We'll go a fairly long ways on SU2 to the k. So we might go out to here. It's only one step, but still, we might go out a distance which is pretty much the diameter of the whole SU2 to the k space. The other one will go someplace else. This one will go someplace else, and this one will go someplace else. Now we go to the next layer. This goes here, this goes here, that goes here, this goes here. Now, keep in mind, this is a very high dimensional space. What I'm drawing here is at best a cartoon, but still, it'll give you some feel. Okay. What is first of all true is the way SU2 gets filled in is extremely fractal. I think this is what you were getting at. It's extremely fractal. It depends on epsilon, but let's suppress epsilon dependence for a minute. It's extremely fractal, and it fills in a very, what shall I call it, irregular way. And in particular, two things can be very close with respect to the inner product metric and be very hard to get to from one to the other through a small number of gates. That's particularly true if the small distance corresponds to e to the I epsilon times a very, very large weight operator. A large weight operator means a lot of qubits. If, for example, to go from here to here required an operation which involved a lot of qubits, then although these could be very close in a product, they can still be very, very far in the complexity space. In that sense, these two spaces or these two metrics are very incommensurate. I don't know if that's the right word, mathematical word, but very, very different. Okay? You look puzzled.
Oh, somehow like that intuition makes me think that complexity couldn't be as universal as it seems to be between two states. Just because like I could choose different generators.
You're asking about the universality. Okay. Right. So there are basically two kinds of ambiguities. One is additive. This is a guess to some extent. I think that's probably a good guess. But I think there are two kinds of ambiguities when you come out to start actually trying to calculate complexity. One is additive and one is multiplicative. The additive ambiguity actually has to do with epsilon. Epsilon always comes in an additive way, log epsilon. Always log epsilon times the dimensionality of the space. There's an analog of that for entropy. Classical entropy, strictly classical entropy. Classical entropy has an epsilon dependence where epsilon means the coarse graining of the phase space. You also draw little epsilon balls in statistical mechanics, otherwise you get infinite entropy. And every state or every configuration has an entropy which is logarithmically divergent in epsilon, Well, you fix epsilon, but it just comes in as an additive constant into the additive constant proportional to the number of degrees of freedom. Here, same thing. There's an additive constant, log epsilon, which is epsilon dependent, but doesn't affect, for example, the way complexity grows or differences of complexity. And then there's a multiplicative ambiguity. The multiplicative ambiguity has to do with, for example, supposing I originally only allowed 2-qubit gates, and then I say, oh, I'm going to now allow 3-qubit gates. Well, every 3-qubit gate can be made out of some number of 2-qubit gates. Okay? So by including 3-qubit gates, you probably simply diminish the number of gates that you need, but by a multiplicative constant, namely something to do with how many 2-qubit gates it takes to make an arbitrary 3-qubit gate. So there's always a multiplicative ambiguity in the complexity and an additive, and we're going to have to deal with that. Well, we're going to have to take that into account. But up to the additive and multiplicative ambiguity, at least when the complexity is relatively large, it seems that it's fairly universal. And I will take that assumption that it is universal, or close to universal. Okay, so these two metrics have very different meanings, very different shape, and very different purposes. Let me just remind you, the inner product measure tells you, what does it tell you? It's the thing that you use in quantum mechanics all the time. When two things are close in inner product measure, it means all expectation values are very close. So if all you're interested in is expectation values, you don't care about relative complexity. On the other hand, if you do care about how hard it is to make a transition from one state to another, or how hard it is to interfere them, then you do care about relative complexity. So they're for very different purposes, they have very different shape, and we'll keep that in mind. Okay, now I said no collisions. Let's see, it's now 12, we have another half hour. Okay. I said no collisions, but of course there will be collisions. You can see it from here. Eventually, the number of leaves will become equal to the number of epsilon balls. When that happens, you can't stuff in any more leaves. You can stuff in more leaves, but they will occur on previously visited epsilon balls. When that happens, you will have loops in the geometry. Okay, so let's see if we can estimate when that happens. That will also define something else. It will define the maximum complexity. The maximum complexity happens when this thing saturates and you simply can't get any more things in without revisiting previously visited epsilon balls, which are known to have lower complexity. So let's see if we can make that estimate. Okay, I lied. I can't erase the blackboard. I just wanted to see Ahmed do it. Okay. On the left-hand side, I'm going to write the number of leaves after a certain depth circuit. That's equal, it's up there somewhere, so I'll just remind you what it is. It is K to the complexity, or the number of steps. That's depth. This is depth times K. K to the complexity, that's the number of leaves. Number of leaves? Yeah. When does that equal the number of epsilon balls? The total number of epsilon balls, I'll just write it again, down again, 2 to the K over epsilon squared, all to the power 4 to the K over 2. This is our epsilon ball estimate of the size of SU2 to the K. What am I writing here? This is nonsense. What I meant to write is that this will define the maximal complexity. The maximal complexity will occur when the number of leaves equals the number of epsilon balls. Is that clear, or should I explain it again? That's just when you fill that up and there are just no more epsilon balls to visit, no new epsilon balls to visit. And now we can solve that. And we find that the maximum complexity, I'll write down what the answer is. It's the most important thing is 4 to the k. Okay, and then there is 1/2. I think it's plus log epsilon divided by log k, if I'm not mistaken. The main thing here is this 4 to the k. What this says is, first of all, it says that the maximal complexity is of order 4 to the k. The other thing that it's saying, or assuming, not saying, it's assuming that, that loops don't occur, or collisions don't occur until they absolutely have to. Now, this is very closely related to the theorem that, that Scott quoted, that he and I wrote, well, which we are supposed someday to write a paper about the rate of complexity growth, that the rate of complexity growth is maximum. This is basically the same assumption. And this is what it says, that the maximal complexity is 4 to the k. Now, everybody who does this sort of thing will agree that the maximum complexity is 4 to the k. I don't know if they'll agree with this level of detail here. But there is a log epsilon. There is also a log epsilon. We'll also agree that there's a log epsilon. This log epsilon is called the Kitaev-Solovay theorem. And in fact, the Kitaev theorem is not as powerful as this. It says there's some logarithm to some power here, unknown power, thought to be 1, thought to be 1. Okay. Let's summarize something now. That the maximal complexity, and you can think of the maximal complexity as, well, we'll come to it. Maximal complexity, it's basically the maximal distance between any 2 points in the complexity geometry. We can call it the diameter, the complexity diameter. The complexity diameter is of order 4 to the k. What about the number of epsilon balls, or the number of vertices? So it comes to the same thing, the number of vertices, total number of vertices up to that point. That's of order e to the 4 to the k. The diameter is logarithmic in the number of vertices that we've come to thus far. Now, what happens next? The next question is, what happens next? What happens when you reach maximal complexity? In other words, when you reach the outer boundaries of the tree, what happens next? Supposing you add another piece of a circuit. You add another single layer of the circuit. You've got to go somewheres. You've got to go somewheres. But we know that you've filled up all the epsilon balls. You simply have to go to some place that you visited before. Now, this is not completely clean. Where you go from here will not necessarily sit right on top of an epsilon ball. You'll wind up somewhere near some previous epsilon ball, perhaps not exactly overlapping with it. Maybe sort of off on the side a little bit. I'm going to ignore that. This is a fake, but I'm going to ignore it anyway to try to give you some feel for what the geometry is like. So the next step will bring you around to some previous place. It will bring you someplace which is not close by. Well, I'll come to that. I'll come to why it can't be close by. But it'll bring you to some other place. This one will go to some other place over here. This one will go to some other place over here, and so forth. And from there, the graph will just continue and recycle previously visited sites. Okay, so what do we know about this overall graph? Assuming that we can fudge. I've fudged a little bit. If a point comes out close to an epsilon ball, just give me the license to move it over to the epsilon ball to get some sense of what's going on. Okay, I have another drawing over here that I like better. The circle here is just guidelines for me. The tree is the important thing. You start at the center. This is a tree of degree 3, but of course we really want a very high degree. The outer boundary of the tree is where the complexity is maximal. Okay. First of all, you can see from this tree that the smallest, all right, it's going to connect up here somewhere. This point may go to this point could go to that point. Let's first ask, could this point over here go to that point? Now, the important thing about this diagram is that it's homogeneous. Every point is the same as every other point. Why is that? Because we're talking about a group space. And, yeah, we're talking about a group space, and so every point is really the same as every other point. Now notice this point over here has no small loops. The smallest loop you could possibly have would be to go out to the full diameter and then come back. There are no small loops, which means that there can't be any small loops up here. This was a fact that was taught to me sort of by Douglas in some slightly different context. I made the mistake of not realizing this. You have to jump. This one may jump to here, this one may jump to here, and so forth. This one may jump to all the ways around to here. So you expect big jumps in this picture, just so that there won't be small loops anywhere. The smallest loop is expected to be about as big as the diameter. What's that?
You don't jump back to close to the origin.
Very good question. Very good question. The answer is that almost all points on here are close to the maximal complexity. Now, can you jump back to the origin? Yes, but remember the total number of vertices is e to the 2 or e to the 4 to the k. Some monstrously big number, and almost all of them are out near the boundary. So it would be very rare and exceptional that you would jump anywhere except to somewhere near the boundary, and we're going to talk about that. Okay, let me write down what we know about this graph. Number one, it's finite. By assumption, I've fudged it so that when I come back to an epsilon ball, I just stick it on top of the previous one, and that's a little bit of a fake. But the geometry altogether, I'll take to be finite. It's finite. It's tree-like about any point. Finite and tree-like. Now, tree-like means up to some distance until you get out to maximal complexity. Finite and tree-like about any vertex. It's deregular. Deregular. This is 2. What does deregular mean? That simply means that every vertex has the same degree, same number of things coming out of it, just the number of independent unit depth circuits. Okay? So it's deregular. What else do we know about it? I'm losing space here. It's sparse. Sparse means the following. What's a not sparse graph? A not sparse graph is a complete graph. A complete graph is one where every site connects to every other site. Okay? Here, the number of and that means that the degree is comparable to the total number of sites. That's called dense. In this case, the degree, if you go back to what the degree was, it's much, much smaller. The number of sites is doubly exponential. The degree was much smaller than that. And so the degree is much lower than the number of sites. It's called sparse. So it's a sparse graph. What else? Its diameter, well, first, its volume, or the number of vertices. The number of vertices is e to the 4 to the k, or something like that. That's the number of vertices or the number of unitaries altogether in the space. On the other hand, the diameter is 4 to the k. So the diameter is like the logarithm of the total number of vertices. And finally, another term, the girth of the graph. The girth is the smallest closed loop, like my girth, okay? The smallest closed loop, and that's comparable to the diameter. Girth, also 4 to the k. Graphs like this have a name. They're very hard to understand. They're hard to build, and they're almost all graphs. The random graphs are like this, more or less. But graphs with exactly this set of properties are called expander graphs. And believe me, I struggled to find out what an expander graph was because it's in the language that I find very unfamiliar. But this is what an expander graph is. The subject of expander graphs is all over the place in computer science, but not for this reason. Okay? So that's what we have here, a geometry which is right invariant, and incidentally, we will talk more about right invariant metrics, and if you're ever interested in them, and you want to read the best possible literature on them, it is Vladimir Arnold's book called, I think it's just called Classical Mechanics, and it's spectacularly clear if you can get it in English. Arnold is, of course, the famous Russian mathematician Arnold. How a Russian got named Arnold, I don't know. His first name is Schwarzenegger. That's what no, okay. All right, the last thing, how much time do we have? We have 15 minutes, okay. Last thing I want to talk about is this notion of a second law of complexity. And just qualitatively, I want to imagine an ensemble of systems. Now, an ensemble can either mean you're doing statistics, you have one system, but you're doing statistics over how it can move, or you can imagine a gas of a large number of systems. Average over the gas would be the same as ensemble averaging the single system, averaging over different ways it can move. Okay, so the ensemble starts with all of its elements near the center. Now let's follow one of them as it moves out. I'll use blue here. It moves out, and moving out, its complexity increases from 0 to k over 2. Next, it has to make a choice where to go. It could go back, but that's very, very unlikely for reasons that were said. So the next place it will probably go is here. The complexity is increased again. Let's draw a graph of the complexity with time. This is the complexity for just a single element of the ensemble. The complexity has gone from 0 to k over 2 to twice k over 2, and so forth and so on. It keeps moving out with extremely small probability that it will move back in, and so it increases linearly for some time. Then it gets out to maximal complexity and finds that it's got to revisit sites. So let's say it goes around, let's pick this one over here. Let me just make it visually exciting. Let's draw it as coming around to here and forget this one over here. Comes around over to here. It may or may not hit an absolutely maximal complex, but it will hit something close to maximally complex. Why? Because there are just so many more things which are maximally complex. So it'll hit some other point over here. It might decrease a little bit. This point may be inward a little bit relative to this point, so there might be a little bit of a decrease here. But what will happen next? In the next step, it will overwhelmingly move outward again. Up it will go. Until it gets out to the maximally complex things. But before we do that, let's just ask what its complexity is when it moves around to here. Remember, the complexity is not the number of steps you took to get there. It's the minimum number of steps that you could have taken to get here. And that would be more likely to look something like this. This will be less steps than it takes to get from here plus here. So all of a sudden, something has happened. The complexity has stopped increasing. The trajectories, or the geodesics, let's call them the geodesics, have changed. Instead of following this geodesic to find the complexity, we follow an altogether new geodesic. And then we follow it a little further. This will again move out to maximal complexity, jump to some other place, which is not even drawn here. And again, the same thing will happen again. The minimal path to get to here might be this. So, first of all, the complexity stops increasing. It can't increase anymore. It takes an exponential time to get there, exponential number of gates. So the time is some exponential of k. The complexity is also, let's say, some 4 to the k up here. And it simply wobbles around up here with the minimum trajectory changing from instant to instant. The whole structure just, the whole structure that led to this linear increase breaks down. And something wildly, radically different happens. Eventually, somebody pointed this out before, eventually, by sheer luck, you might, you might get to some place where after a series of steps, you get back to the origin. Now, that's incredibly unlikely, doubly exponentially unlikely. The amount of time that you would spend hovering around here before you would make one of these sort of freak reversals back to low complexity is the recurrence time, in this case the quantum recurrence time, which is not e to the k, but of order e to the e to the k. And when that happens, you might come back and revisit the origin. These are quantum Poincare recurrences, or quantum recurrences, and these just take forever. But if you have one and you look at it, you'll see two things. You'll see an initial period in which the complexity decreases, pretty much following the time reverse trajectory here, hitting the bottom. I've constrained it. It doesn't hit the bottom easily. I said, suppose it does hit the bottom. Then it'll track back and go up again. Going up again will follow the same trajectory here. So you'll find intermittently, very rarely, but intermittently, structures which look time reversal invariant about the center here, which go down and come back up. The implications of that for black hole physics are fascinating and interesting, and we'll come to it. All right, I think it's probably time for me to finish. I'll take any questions for the next 3 or 4 minutes, if that's okay with Juan. Is it okay? I think, yeah, I do have 5 minutes, right? Yeah, okay, so, yes.
Is hyperbolic disk like a good analogy for it?
Yes, the hyperbolic, very much so, I should have said that. Yes, what a tree is like a hyperbolic geometry, insofar as the way that it grows as you move out. Okay, so if there is a continuum version of this, which I think there is, the continuum version of it would have a very hyperbolic character. Every point would be surrounded by a hyperbolic space, but globally it would have this come back on itself behavior that's very hard to envision. The whole thing is very high dimensional. It has this character of being a expander graph. In the notes that I sent to Juan, there's a picture in there somewhere of some expander graphs. They're not very illuminating. They just look like hash, but they are expander graphs. And in fact, one of them is a very special kind of expander, which I think these are. the more sparse the more they satisfy these basic conditions that I wrote down, the stronger they satisfy them, up to some point. If they satisfy them very strongly, in other words, if they grow very quickly and have these properties in spades, let's say, they're called Ramanujan graphs. They have, as far as I can tell, nothing whatever to do with Ramanujan, but they're just really, really good. Anybody here who knows about expander graphs? Douglas, you mean you don't know about expander graphs? I thought you did, okay. Anybody? Isaac, do you? A little bit, okay. The most expanderish kind of expander graph is called a Ramanujan graph. It means it practically saturates the maximal growth rate, which is the growth rate for a pure tree. And in that case, or not practically, it actually exceeds it up until the time it gets out to the boundary. Those are called Ramanujan. I think these are likely to be Ramanujan graphs. Is Henry here? Henry?
I would say that these are Cayley graphs, but only
they're sort of fake, they're sort of fudged Cayley graphs, right. So Henry has a very, very beautiful construction which is not the true quantum complexity. Instead of unitaries, am I allowed to say this?
Yes.
Okay. Instead of unitaries, he studies a classical problem which is permutations on computational states instead of unitary operations, and studies exactly the same things which I've described here for the permutation group instead of the unitary group. And there really is a Cayley graph. Cayley graphs. Those definitely have the expander property, right? Okay, so we do know a little about it. Okay, that's next time black holes, and then the third time back to the second law. Good.